Hey, this is the water sensing team, and we'll be working on the project Water Level Detection System Based Antenna, with our product owner being Stanley. So this is our project outline. In Sydney, we have recognized the problem of flooding in certain areas. We wish to tackle the problem by detecting water level rises before a major flooding happens. In order for this to happen, we need the system to work in complex environments. We need it to be a reliable system that can predict future water level rises based upon previous flooding patterns. And in saying this, we will need signal capturing and processing techniques to be implemented in our final product.
On the hardware side, we use SDR signal generator and annotators to capture the signals. On the software side, we use Python and MATLAB to process and analyze the signals. Specifically, the Python script reads the IQ data, which is stored in a complex format by the SDR. We then apply a fast Fourier transformer to convert the time domain signal into a frequency domain signals, which help us identify the frequencies of the radar reflections, which are related to distance. We visualized the result using MATLAB to display the frequency spectrum and calculated distance. In addition, we use MATLAB for similar signal processing tasks. In MATLAB, we follow the same radar equation principles to read the IQ data, perform a fast Fourier transformer, and visualize the frequency and distance components.
For the mathematical principle of radar and why we use chirp signal and why we need FFT in our project. We use the chirp signal in our project. We send that, and after that signal hitting an object and bouncing back, we use antenna to receive that signal. So once we do some signal processing, such as differentiation of that to chirp signal, we can get a constant frequency signal line, which is the green line on the graph. So that frequency is only related to the distance between object and water level. So that means once we found the frequency of that green line, we can find the distance between the object and the radar.
This code processes radar signals captured as IQ data. First, it imports necessary libraries like NumPy for data manipulation and Matplotlib for visualization. The IQ data, which contains real and imaginary parts of the signal, is loaded from a file. So the fast Fourier transformation, or FFT, converts this time domain signal into the frequency domain, revealing frequency components of the radar data. A frequency axis is calculated then for plotting purposes. The resulting spectrum is plotted to visualize signal magnitude against frequency. Finally, this code calculates distances based on frequency shifts using the radar equation. Constants like the speed of light, chirp bandwidth, and chirp duration are used to derive distances, which can be plotted or analyzed further. This is basically the backbone of radar signal processing for distance estimation. Okay, so this MATLAB code processes radar IQ data similar to the Python version, but leverages MATLAB's built-in tools for simplicity. So first, the IQ data is loaded. File contains complex float 32 values, with each sample representing real and imaginary components of the radar signal. So the SDR handles communication with base stations, simplifying data collection. And then once loaded, we determine the number of samples and set the sample rate. So here it's assumed to be about 2.4 megahertz. So next, an FFT, fast Fourier transformation, is applied to convert the signal from the time domain to the frequency domain. The FFT shift function centers the zero frequency for better visualization. Frequency axis is then calculated, spanning from negative to positive frequencies. The frequency domain data is then plotted, showing signal magnitude in decibels versus frequency. And then this graph highlights the key spectral components of the radar signal. Finally, distances are calculated using the radar equation. Constants like the speed of light, chirp bandwidth, chirp duration enable conversion of frequency shifts into real-world distances. This assumes no path loss, idealizing signal propagation. The resulting distance data is plotted against magnitude to visualize the targets detected by the radar. And in the next slides, we'll see how that kind of looks like.
For our current progress, we successfully use SDR and antenna to capture the raw signal, which is the first diagram. But you can see there's not many useful information in that graph. And after we use fast Fourier transform to process the raw signal, we get the second and third diagram. For the second diagram, that's from the 4G and 5G Sirius band. You can see it got a really high pulse at 900 megahertz. That means we capture the signal of the 4G Sirius band. And for the third one, you can see it's for the FM radio. You can see it got strong amplitude at 90.5 megahertz and also at 90.9 megahertz. That's two frequency. It is the FM radio around my house. So that means we successfully capture these two FM radio by using antenna and SDR. For our future step, because we already used antenna and SDR to capture the useful information signal from the environment, such as 4G, 5G bands, and also the FM signal like 90.5 FM radio or 90.9 FM radio. So that means our receiver is correctly work. So our next step is using the signal generator to test the water level data, like combine receiver and signal generator together as the one project. And also after that, we also can write and embed water level prediction code into our system, and that is the entire system of our future step.